Oh, so left, right, great, okay. Thanks a lot. So I want to talk about some work I've been doing quite recently. I started this project in the autumn of last year, and it's about. Sorry, I'm going to unmute. Yep, I'm unmuted. This is a problem I started in October last year. And it concerns two separate scientific puzzles, which I'm going to argue are intimately related. And one of those is something called the simplicity bias in input-output maps. And the other is this sort of seemingly observed tendency for learning mechanisms, learning platforms, to have a built-in Occam's razor. Meaning that, that just as Occam's razor tells us, it prescribes the simplest explanation that fits the facts, it seems that learning platforms are biased toward the simplest outputs that meet the constraints. So I'll speak a little bit more about that. So I'm going to start off with input-output maps. So again, we've got your arrow doesn't go to the next slide, but I'm sure we can solve that. So it was left and right, now it's up, down.
Up and down.
I see, but now down doesn't work either. Look, that's down. So
strange. Then no. Works.
Yes, but you better stay there because it won't work in 30 seconds, but okay. So input-output maps. So an input-output map is a very general concept. Think of an input as your instructions and your output as a function. Your input is like a computer program, and your output is what that computer program does. Your input you can think of as a genotype, your output is a phenotype. Now input-output maps tend to be very degenerate. There are way more inputs than there are outputs, many more instructions than functions. So, a classic example, well, I'll mention a few examples. Here we've got, let's see if we can get a bigger zoom in on that. So here's an example that was observed empirically by a team in Oxford several years ago. So look at protein self-assembly, protein complexes. So proteins self-assemble to do things like create virus shells. Now here, if you just look at all the, a collection of known protein complexes, and you just plot their frequency, how often do they show up? So the frequency is on the y-axis, and here we're just looking at the complexity on the x-axis. So notice that the most frequent complexes have the greatest symmetry. So two of them have this hexagonal symmetry, and these two are a sort of a prism, a triangular prism. The least frequent complexes are irregular shapes that you see down here. Now here, the authors did just a simulation of self-assembly with polyominoes. These are just, on a square lattice, you self-assemble. So, what do we mean by self-assemble? You just have, you have different species of squares with different parapotentials. Here, green and yellow. Yellow is attracted. Little a likes big A, so it self-assembles to this. By self-assemble, meaning you put a bunch of these particles in a box and you shake. And you get this shape when you do that. Now, if you look at all possible ways of labeling these, all possible parapotentials, and for each one, shake a bunch of them up. What shapes do you get? Well, you sometimes get highly symmetric shapes like this, and sometimes irregular shapes like these polyominoes. But these ones show up much more frequently, meaning they're much more designable. There are many more sets of these squares and parapotentials between them that lead to these symmetric shapes, right? So it turns out that this is a fairly global, pretty global phenomena when you look at RNA secondary structure. So RNA, you have these 4 nucleic acids. They form into these hairpins and loops. But the most frequent RNA shapes, when you look through a pulsable RNA, are highly symmetric objects. This is just one hairpin in a loop, as opposed to less frequent asymmetric objects. So again, we seem to have this exponential bias towards simplicity. And the same thing happens when you look at simple models like circadian rhythm or L systems, which are these formal grammars for creating like fractal shapes. And in general, one of the consequences these authors argued, and of course this is all empirical, is that this effect is so strong that you can imagine evolution without selection. What is evolution? It's inheritance, mutation, inheritance, and selection. But this paper argues, or conjectures, that there's so many more ways of designing very simple, symmetric things that selection plays a less strong role. In other words, you could argue this is you could say this is an argument strongly in favor of convergent evolution. Now, I was interested in this, and instead of just looking at empirically, I wanted to look at it more formally and try to say something, prove something, and predict something about why we see this simplicity bias in input-output maps. So I became interested in the archetypal, what I think is the archetypal input-output map, a deep layered machine. And here, what do I mean by that? I mean, we've got k nodes wide. So this is k equals 2, k equals 3, k equals 4, and so on. We're going to have n layers deep. And what I want to do here is put a random Boolean function at every node. Right? I want to put a random Boolean function at every node and see how does this, as we increase n, what does the distribution of Boolean functions look like? So it's a super simple problem, right? Let's look at. So let's just try to understand the k equals 2, right? Because if we can understand k equals 2, I think we'll unlock the whole problem and be able to say something quite general about input-output maps in these deep layered machines. So for k equals 2, well, there are 2 to the 2 to the k, so 2 to the 2 to the 2 equals 16 Boolean functions. Here are some of them. So here are our inputs, and here we've got, the AND function, the OR function, the exclusive OR function. And I'll just tell you briefly the history of dynamical systems with Boolean functions. That's probably one of the earliest studied ways of looking at dynamics. In the 60s, this was put forward as a simple model for describing genetic computation, in particular genetic regulatory networks. Someone called Stuart Kauffman said, look, why don't we, it seems as though activation and inhibition is what dominates these gene regulatory networks. And he put forward something called the Kauffman model, which became this sort of cult object in statistical physics. And over the last few years, I did some work on this. But now I want to look at a much simpler problem than the Kauffman model. And that is these deep layered machines. So just coming to k equals 2, let's look at k equals 2 for one layer. So, right, I just want to say f is a function of g1 and g2, which are each functions of a and b. So how do you do this composition of Boolean functions? Well, you do it in the same way that you do composition of ordinary functions. So here are a couple examples. I'm going to set f to be, I'll set g1 and g2 to be a or b for g1, and not a and not b for g2. And then if we set f equal to g1 and g2, well, we can plug them in. So we get f is equal to g1, g2, plug in g1 and g2, multiply them out, and this is what you get. You get exclusive OR. But if I change f to be XOR, exclusive OR itself, and you plug these in, then you just get f equals true. The point is that, Boolean composition is easy to work out case by case, but can we say something? Can we say a general theory of this? Because this will unlock our understanding of deep layered machines. Well, how many different ways are there to play this game? There are 16 choices of f, 16 choices of G1, and 16 choices of G2. So let's just plug those all in. So here, these 16 panels, these are our different choices of F. There are 16 Boolean functions. And on each one of these panels, the x-axis is G1, 16 choices. The y-axis is G2. And what the output of this is just indicated by the grayscale of this. So there are 4,096 things leading to 16 different output Boolean functions, because ultimately F has to be a function of A and B. So here are the probabilities, right? We just work this out exactly. So for a k equals 2 model, for n equals 1 layer, so we just have one depth n equals 1, these are the probabilities that we have these different Boolean functions. This is A and B, A and not B, not A and B, copy A and ignore B, A and B exclusive or A and B. This is just A or B. And we can work out these probabilities. We can work them out by hand. And one thing that you see is that the probability of a deep layered machine only depends on something called the Hamming weight of the Boolean function, which is just the number of ones in its truth table. So, okay, well, that's n equals 1. Let's say we take 2 layers. We have now one more layer. Well, the probabilities get a little bit weirder, and we do it again. N equals 3. You can work these out. Well, can we create a theory for this? Well, here's the same thing for k equals 3 inputs, right? So now we have 256 Boolean functions. And again, you can work these out in principle. These numbers get bigger and bigger. Here I've sort of shown, I plotted what these look like for k equals 2 and 3 and 4 inputs. And here for each one, we see that the number of layers increasing. So n equals 0, n equals 1, 2, 3, 4. And what we're doing here, we're just plotting, the probability of Hamming weight 0 is 1/16. Probability of Hamming weight 1 is 4 times 1/16, 4/16. There's 6 of these, so it's 6/16, 4/16, 1/16. And then we carry on. Well, here we've plotted n equals 0, which I just described, n equals 1, n equals 2, and so on. And what we see is that this distribution starts to flatten out, but also true and false start to jump up. Look again at k equals 3. The distribution flattens out, true and false start to rise up. K equals 4, the same thing happens, it flattens out, but true and false rise up, but a little bit more slowly this time. Well, after hiding myself in a cupboard in my office for a few months, I worked out an analytic expression. So this entire system can be described, the entire sort of distribution of a deep layered machine can be described by this very beautiful matrix. I think it's like super cute. So here's the matrix. I mean, you describe it in words. This is for k equals 2, right? But you can see this is k equals 1, k equals 2. You can generalize it to k equals 3. I'll explain the k equals 2 one. Well, you've got a number I to a power j. Here, it's 0 and 4, 1 and 3, 2 and 2, 3 and 1, 4 and 0. Whereas the exponents, they are constant across, but they increase as they go down, and this one decreases as it goes down. So it's in principle, a super simple matrix. But understanding this, and if we want to understand the nth layer, we just raise this matrix to the nth power. So this is kind of, when I thought this would be impossible to find a solution to this. Turns out you can, and this is what it looks like in principle. Well, what can we say about it analytically? Well, it turns out you can write down the principal eigenvectors and eigenvalues of this thing. So this is just sort of undergraduate mathematics at this stage. And the behavior is dominated by the first 3 eigenvectors. So the first one, the first 2, is telling you about true and false. And the third one is telling you about everything else. And what goes on in this is that true and false slowly become more and more likely. So after an infinite number of layers, no matter how many inputs you have, at infinity, these deep layered machines will only just give true or false. But it takes a long time for them to do that. Now here, I plotted something. I've kind of put this in the language of these input-output maps that you saw at the beginning, where you have frequency and the complexity. The complexity here is just the information content of the output. And this is the log of the probability. And so what you see is that in each case, here we have 4 inputs, 6 inputs, 8 inputs. You start off, and all of the, at n equals 0, because you're putting a random Boolean function and everything, at n equals 0, every Boolean function is equally likely. But as we increase the number of layers, the depth of the network, you see this horizontal distribution, it starts to rotate. It starts to rotate upwards, meaning the simplest ones, because this is the information content in bits along the x-axis, the simplest ones become more and more frequent. But once you get to a certain sort of critical network depth, then you see the whole thing starts to fall down. What's going on there? Well, true and false are starting to take over, right? So this is really strange, the fact that you get these two different timescales in these things. So what that's telling you is it's telling you that there's this critical network depth, right? There's this critical network depth after a certain critical number of layers. You get this maximum input-output simplicity bias. But then the everything diminishes and true and false take over, and then the network starts to become boring. Well, you can work that critical network depth out just by sort of saying the true and false match the interior. And you find that the simplicity bias is maximized when the number of layers is 2 to the power k. This is just a sort of a small constant, so that's negligible. So after I did this, because I know some of the authors of this, they're based in Oxford in the physics department, I saw a paper that came out with an extremely similar title, which I hadn't seen. But what they were doing is they were looking at this not from a sort of mathematical analytic way, but they were looking at this purely empirically, looking at both deep layered machines and deep neural networks. And they find a similar sort of phenomena. Well, what I think is going on here is 3 things. I mentioned 2 of them here, and I'll describe the other one. So I like to think of learning as an input-output map with a constraint on the output. So, I'll give you 2 examples of that I like to use because they're concrete. One is a simple associative memory. So let's say I want my associative memory to turn dog-like images to say dog, and if it's a cat-like image, to say cat. Now, if I give you an image and it looks like a table or a cup, you don't really care what the associative memory does. You just want things in the vicinity of the dog to go to dog, and the vicinity of cat to go to cat. So there's a huge amount of leeway and flexibility for all these things which are not like either of them. Now, my proposition, what comes out of this research, this thing I've just described, is that a deep layered machine or deep neural network, it will give you the simplest neural network that gives you this associative memory. It puts dog-like images to dogs, cat-like images to cats. Everything else, it'll maximize the simplicity for that. Another way, another example is, training a protein to fold to a particular a particular shape, right? So this is sometimes called the inverse folding problem. And it's sort of, famously hard. People in the 90s started to understand it. So if I ask you to, when we're training a protein, what do we need? Functionally, we need a certain active site on that protein. A certain part of that protein has to have a shape, a particular shape. It might unlock something. The rest of the protein is scaffolding, so you don't really care what's going on there. So by the same argument, these deep layered machines are biased. The most likely protein sequence that you're going to get is going to give you a conformation in which it has the constraint, but the scaffolding is maximally simple, right? So it satisfies Occam's razor in that sense. To describe this research in a different way, some of you may know a bit about homograph complexity, sometimes called algorithmic information content. It's sort of a kind of a fun subject. It's a bit of a messy subject. There aren't that many elegant results. But there's one super elegant result, which you can derive in half a page, and it's in most information theory books, and you can say this rigorously, that the probability that you could compress an arbitrary binary string by s bits is 1 over 2 to the s. All right? So the probability, most strings you can't compress, half of the strings you can compress by 1 bit, a quarter you can compress by 2 bits, and so on. But if you look at the output of a deep layered machine, so it's a binary string, the probability that you can compress it by s bits is a constant. It's independent of s. It's just equal to 1 over 2 to the k plus 1. This is the number of inputs. So that's pretty striking. That's a formal result that comes out of this. Now, I want to make a sort of conjecture and just say that simplicity bias, which we see in biological systems, particularly when you have thermodynamic processes like protein folding, RNA folding, protein self-assembly, whether you see it in iterative deep layered machines or neural networks, my conjecture is that this is not an exception, that this is a natural consequence of repeatedly applying a simple dynamical process over and over and over again, a process which is irreversible. The irreversible aspect means that you're going to make it many to one. And that every time you iterate these processes, you're sort of baking in a little bit more preference for symmetry. So the simplicity bias you can think of as really a symmetry bias and the sort of outputs we have. And I think this doesn't just apply to, naturally observed things. I think it also applies to man-made things. So think of the evolution of technology. My favorite one of my favorite authors, probably my favorite, is, or thinkers on technology, is the founding director of the Santa Fe Institute, someone called Brian Arthur. And his definition of a technology is, he says, a technology is a combination of more primitive technologies that harnesses a scientific principle. But his point is that technology is recursively defined. Technology is a combination of more primitive technologies, each of which is a combination of yet more primitive technologies. Now, and I would say that the same thing applies in this case, that as you have, a highly advanced world in which you've got many layers of technological sort of recursion, I mean, we have quite a few, if you just look at, your phone, that you will have as well a simplicity bias that emerges in that sense. Or to put it another way, you would expect that technological innovation would be convergent towards certain fundamental technologies. So I'll stop there. Thank you for your attention. Getting my water, but go ahead, I'm listening. Sorry. No.
And the second is you talked about man-made. I prefer manufactured to man-made. Those things are mainly made for human use, so they're designed for humans. And humans are completely symmetric. Right-handed, for the most part, our brains are asymmetric. So there are other things driving asymmetries and going against simple simplicity.
Yes. So with respect to technological innovation, so one question that emerges in this whole in Braunauth's theory is that certain technologies become more and more robust, more and more predictable, and we start to think of them as building blocks for future technologies. So think the touch screen. Right now, we sort of think, well, that's a building block, and then that becomes these stable building blocks. They can become embedded in future technologies, and if that becomes a very useful building block, they can be embedded. So it's this forward recursive argument that the most powerful technologies to create now are the ones which will unlock future technologies, will themselves unlock future ones. So, but I do agree with you that the role of symmetry, is how you can't push that too far because, life does require a certain amount of asymmetry. Otherwise, nothing emerges. So it's a nice sort of thing. Where do you balance the right amount of balance between symmetry and asymmetry?
Can you tell us a little bit about the Kaufman model and how this sort of fits into that context?
So the Kaufman model was a simple model. It said, look, let's study a Boolean network in which, say each one of us here, was happy or sad, and each one of us had only two friends randomly chosen from the room, and I am happy or sad based on the mood of my two friends. So I only listen to two different people, and I am, and each of you listen to two different people randomly, and we just iterate this system. Now, Kaufman's argument that there is a special transition between order and chaos in this model system, and that life happens, interesting stuff. In particular, life happens at this boundary between order and chaos, and this is called the critical Kaufman model. That happens when k equals 2. I only have two friends. Each of you has two friends you listen to. Similarly, you see this, with Wolfram's elementary cellular automata. The ones capable of universal computation are right at this edge of order and chaos. This in some ways is a simpler. This fully connected Kaufman model is in some ways simpler, right? Because everything's connected to everything. In some ways, it's more complex. That talk about what?
Over-parameterized networks.
Yes.
And why over-parameterized networks have bias for flatter lemmas, which can be generalized better than sharper lemmas. But in machine learning, you also do some learning with a learning algorithm. Whereas here, you have a Boolean network, and you're basically talking about the simplicity based on inputs and outputs and things of that kind. But when you add constraints instead of considering all possible inputs and outputs, like what happens?
Yeah. So this paper that I mentioned in the beginning, argues that in evolution you could have this bias toward simplicity because whenever you look at the space of possible mutations, that you're much more likely to lead to something which is slightly simpler, but it still possesses the same phenotype, so still does the same function. Now, I would argue that even because some people would say, well, this is true in the null model random case, but what about the highly tuned realistic, deep layered or deep neural networks, which are very much trained to do a specific thing? I would argue, and I would say it's most likely that with, you know, as you in the sort of the, you know, the adjacent possible of that, any sort of perturbation from that, and these things, you get to these solutions by slowly perturbing them, you're still going to have this bias towards simplicity. Meaning the null model and the sort of the tuned model, I think, won't be qualitatively different in terms of this bias.